All right, today what we're going to be looking at are more tests for whether or not something, a series in particular, I shouldn't just say something, we're looking at series, whether a series converges. Now, you'll remember that last week we talked about what a series is, what it means for a series to be convergent, and we looked at a few different tests for whether a given series is convergent. For instance, we saw how you can deal with geometric series. Actually, geometric series are particularly nice because not only were we able to see whether or not they converge, but we were actually able to give a formula, right? We had a times 1 over 1 minus r. We have this formula for what the series has as its limit. So we know how to deal with geometric series. And then we also saw that there are a few examples that are particularly nice. Another simple example that we could deal with was the case of the telescoping series. You know what? Give me a second here because I'm having major issues with my board today. Okay, so my whiteboard keeps falling off the wall, and hopefully that won't keep happening, but I wanted to add some additional tape just to hopefully keep things in place. So telescoping series, those are pretty simple. Those are ones where the terms kind of keep on canceling each other out. And so the whole series just kind of can be thought of as this sequence. And then we also had a test called the integral test that we were able to use. And the integral test was actually, the integral test, remember, said the following. Suppose that we have the sum from I equals 0 up to infinity of these xi's, or whatever you want to call them. Actually, let's call them something other than the xi's. Let's call them ai's, because I'm going to use x for something else in a moment. And suppose that these a sub I are bigger than or equal to 0, and a sub I plus 1 is always less than or equal to a sub I. In other words, the sequence of terms that we are summing, these a sub i's, they form a positive decreasing, or at least non-increasing sequence. Then what we are able to do is, if f of x is a decreasing function with f of I equal to a sub I, then the sum from 0 up to infinity of the a sub I converges if and only if, which we often in mathematics, to write if and only if, we write IFF. So this means that the implication, the logical implication, goes in both directions. It's not just if this is true, it's also only if this is true. The integral of the fx converges. Now, actually, there's more that we can observe about this integral test. So, for instance, a series can actually be thought of as a sort of an integral. And the way that we can think of this as an integral is that really the sum, and I'm actually going to do the sum from 1 to infinity here just for simplicity. Actually, it doesn't really matter. We'll do 0 to infinity of these a sub I. If g of x is defined as the piecewise defined function that is equal to a sub I for I less than or equal to x less than I plus 1, then this is actually equal to the integral from 0 to infinity of g of x dx. And it's not too difficult to see why this is true. The reason that this is true is because on each of these intervals, if I look at y equals g of x, well, this is just going to be a 0, and then we're going to have a 1, and then we're going to have a 2, and so on. And in fact, this sum is really just going to give me the area that is in total under all of these rectangles. And of course, we're going to keep on going here. But that's the same as the integral of this g of x function. So you can actually think of these infinite series as kind of integrals in their own right. And integrals of these piecewise constant functions, those are what give rise to these series. So the integral test really just comes from the fact that the integral of f of x is going to be smaller than, like, the area under this f of x curve is going to be smaller than the area under these rectangles. But also, if you were to bump f of x over by 1 and then think about this, well, then the area under this f of x curve is going to be bigger than the area of these rectangles minus the first rectangle. And therefore, either they both converge or neither of them converge. By the way, there's one more observation that I want to make. I'm making a bunch of observations here, and they're not entirely necessarily in a completely sensible order, but then there really isn't a good sensible order for this. One other observation that I want to make is that this, and this is true in general, the sum from I equals 0 to infinity of a sub I converges if and only if the sum from I equals k to infinity of a sub I converges. And k here can be any constant. So what does this mean? What it means is I can cut off a finite number of terms at the beginning of a series, and it doesn't change the convergence properties. Now, this is not really surprising, because all this is saying is that if I'm adding up an infinite series, that's the same as adding a finite number of terms and then throwing the rest of the infinite series into there. That isn't going to change anything. So we can always cut off the beginning of a series if we need to. This is actually something that's really useful in a lot of situations. In many situations, we actually will look at a test, and the test might have some kind of condition on the series. But that condition may not actually be true for the series we're interested in. However, in some cases, what you can show is that the properties do hold if we cut off the series after before a certain point. So what we do is we say, okay, this property is not true of the series in general, but it is true as long as we cut things off before a certain point. If we throw out the first few terms, then the rest of the series will have this property. And a fairly simple example of this kind of thing would be if we had something like the sum from I equals 0 to infinity of a sub I, where a sub I is going to be equal to, let's say that it is equal to I for 0 less than or equal to I less than or equal to 5, and then it's equal to 1 over I squared for I bigger than 5. Well, the thing is that for I bigger than 5, this is a P series with P equals 2. And we know that such a thing converges from the integral test. But the first 5 terms, it's not a P series. But the thing is, we can just ignore those first 5 terms and look at the rest of the series. That converges, and therefore the entire series is going to converge as well, even though these first 5 terms are something totally different. Okay, so this is kind of one of those examples where you throw out the first few terms, the rest of the series has some nice property, and then you go with that property and use it to show that the whole thing has to converge. We'll see more examples of this kind of thing later on. I just wanted to show you a really quick sort of, I know this is a bit of a contrived example, but I wanted to show you anyway just to kind of make sure you saw something involving this kind of stuff. Okay, so what I want to focus on today, and I'm going to do things a little bit out of order from the book here. The reason I'm going to do things a little out of order from the book is because I really think that this order makes more sense. In fact, I'm not too happy with the order that the book does these things in. So the thing I want to look at now is something called absolute convergence. And then we're going to look at something called alternating series. Now, the thing about absolute convergence is that it turns out that absolute convergence is a very strong condition, but it's also one of the easier ones that we can test for in some ways. So it's really important. But it also turns out that it has some very interesting properties to it. So here's what absolute convergence means. We will say that the sum from I equals 0 to infinity of a sub I converges absolutely if the sum from I equals 0 to infinity of the absolute values of the a sub n converges. In other words, you're summing not the a sub i's anymore, or why did I put an n here? A sub I, because we're using I as our index. You're no longer summing the a sub i's themselves, you are summing the absolute value of these a sub i's. Now, the important thing about absolute convergence is this. So let's state this. If the sum from I equals 0 to infinity of the a sub i's converges absolutely, it actually converges as well. So the series is going to converge if it converges absolutely. And the proof of this fact isn't super tricky, so let's talk through why this is true. So notice that the absolute value of an is equal to either an or minus an, depending upon whether we're talking about something that is positive or negative. And so what we can say is that 0 is less than or equal to a sub n plus absolute value a sub n, which is less than or equal to 2 times the absolute value of a sub n. And so what we can now do is we can say that since the sum from I equals 0 to infinity of absolute value of a sub I converges, so does the sum from I equals 0 to infinity of 2 times the absolute value of a sub I. Because we're just multiplying everything by 2, that just changes our limits by a factor of 2. And then what we can do is we can say, okay, so this means that the sum from I equals 0 to infinity of a sub n plus absolute value of a sub n converges. And why is this true? Well, the reason is because of something that we'll talk about in more generality afterwards. But there is what is called the comparison test. So if I have two series and they both consist only of positive terms in the sequence that's being summed, and one of them has terms that are less than or equal to the other, and the one with the larger terms converges, well, then the one with the smaller terms has to converge as well. It's kind of like the squeeze theorem, but for series, because essentially what we're saying is this series with the smaller terms is going to form, the partial sums will be a bounded increasing sequence, and therefore this converges. But this means that we can write that the sum from I equals 0 to infinity of the a sub i's, I don't know why I keep writing an n. I think it's because in my notes I often have n's. The sum of these a sub i's is equal to the sum from I equals 0 to infinity of the a sub i's plus the absolute value of the a sub i's minus the sum from I equals 0 to infinity of the absolute value of the a sub i's, and therefore this thing converges, since it's the difference between two convergent series. So we will return to this when we discuss the comparison test, which we're going to be discussing very soon. In fact, why don't we really briefly talk about the comparison test right now, because it's not too complicated and it's worth taking the time to do. So here is the comparison test. The comparison test, suppose that we have a sub I and b sub I are bigger than or equal to 0, and we also have that ai is always less than or equal to bi. Now notice, I'm not saying that every one of the a sub i's is smaller than every one of the b sub i's. I'm just saying, like, a5 is less than or equal to b5. a6 is less than or equal to b6. But notice that, like, a5 might be bigger than b6. And that's fine. It's just when they have the same index, the a sub I needs to be the smaller one. And the terms have to be positive. Well, in this case, then if the sum from I equals 0 to infinity of b sub I converges, so does the sum from I equals 0 to infinity of the a sub I. And here is why. Let's suppose that Sn is the partial sums for the b sub I series, and Sn prime is going to be the partial sums for the a sub I series. Well, then what we can say is that Sn prime is an increasing sequence because all of the a sub i's are bigger than or equal to 0, and Sn prime is always going to be less than or equal to the sum from I equals 0 to infinity of these b sub i's. The reason being that the partial sums for the a sub i's are bounded by the partial sums for the b sub i's. But this means that these partial sums are an increasing sequence that is bounded. A bounded increasing sequence has to converge in the real numbers. And that means that the sum for the a sub i's converges. Because remember, the sum for the a sub i's is just the limit of the partial sums. So the comparison test is not really all that complicated to understand why it's true and to prove it. Now, before we return to the absolute convergence stuff, I just want to point out what are some situations where you can use the comparison test. Well, a good example of using the comparison test, let's suppose that I want to show that the sum from I equals 0 to infinity, or actually let's do I equals 1 to infinity just because I want to make sure that nothing weird happens here, of 1 over I squared plus I converges. Well, the point is that we can do this by the comparison test. So notice that 1 over I squared plus I is always less than or equal to 1 over I squared. But the sum from I equals 1 to infinity of 1 over I squared converges by the integral test. Now, I'm not going to actually do the integral test out for you. I'm going to let you see that the integral test can be done here. So if it's not clear to you why that's true, take a minute, go back to looking at the stuff we had about the integral test and, check that again, because it is important that you understand why this is true by the integral test. actually this is just a p-series, and so it's, it's a standard sort of thing. So go back and make sure you see that. Anyway, so in this case, what we can say is that by the comparison test, the sum from 1 to infinity of 1 over I squared plus I also converges. Now, this doesn't tell us what it converges to, although we do know it's going to have to be something less than or equal to whatever this series that we're using for the comparison converges to, okay? So we do know that, but we don't know exactly what it converges to. And actually, this is something sort of philosophically that we encounter a lot with series. There are many series where it is possible to show that the series has to converge, but it is not possible to give a nice expression for what the series converges to. We may not be able to figure out where it actually converges, but we can say it does converge to something. And that's often good enough. So, you might think, well, that doesn't seem very useful. Shouldn't we be getting an actual answer here? No, we don't actually need the number that it converges to in many situations. From an abstract math perspective, it's often good enough to be able to say this limit exists without necessarily saying what this limit is. And even from a practical applications perspective, like let's say you're an engineer and you need to compute some series. Well, here's the thing. You don't need the whole series. You just need an approximation for the series, most likely. And you can usually approximate the series by just taking some finite collection of terms and summing them up. The reason being that, if the series converges, then the tail of the series has to be getting very small. And so for most practical purposes, it's good enough to just say, let's go ahead and approximate the series, and that will be enough. So mathematicians often only care about the fact that the series converges and don't really care what it converges to necessarily, whereas people like engineers who are interested in what the series converges to often don't care about what it converges to exactly, and therefore they're okay with an approximation. So for this reason, we actually don't really care too much in a lot of situations whether we can figure out what the series converges to. Now, sometimes you can, and the proofs can be very interesting. In fact, I want to remember later to post something about the convergence of certain p-series. There's some interesting results here due to a mathematician named Euler that he was able to compute exactly what these p-series came out to. Well, in some cases. Now, we can see which p-series converge using the integral test. That's very easy. But seeing what do they converge to, that is not at all obvious. Okay, so this is the comparison test. Now, the problem with the comparison test is that frequently it's rather difficult to come up with something that will actually work with the comparison test. So the problem is that, like, in that particular example, what I said works just fine. But note that this would not work. The comparison test wouldn't work if I had something like the sum from I equals 1 to infinity of 1 over I squared minus 1/2 I. Because the problem now is that 1 over I squared minus 1/2 I is bigger than or equal to 1 over I squared. So the comparison test doesn't work. Now, that doesn't mean the comparison test is bad. It just means it doesn't work in this particular situation. And so, when it works, the comparison test is great. It's very straightforward. It's usually pretty easy to check. The problem is that you got to come up with something where the comparison test actually applies, and that may be a somewhat tricky proposition depending upon what you're actually dealing with. So, that's just kind of a limitation on it, and yeah. So let's move back to talking about this absolute convergence idea. Now that we've seen that absolute convergence implies convergence, we can say more things about what does absolute convergence actually tell us. Well, one of the reasons why we are interested in absolute convergence is because if I'm looking at the sum from I equals 0 to infinity of a sub i's, if we consider the sum from I equals 0 to infinity of the absolute value of the a sub i's, then these absolute value a sub i's are always bigger than or equal to 0. Now, why does this matter? Well, the reason it matters is because think about something like the comparison test. I said the comparison test only works if you're dealing with a series whose terms are all bigger than or equal to 0. And it turns out that there are a bunch of other things, other tests that we will see that either only apply when the series involves only positive terms, or that only test for absolute convergence. So it turns out that a lot of times we can test for absolute convergence more easily, in some sense, than we can test for just convergence by itself. And yeah, so that is one of the reasons we are interested in absolute convergence. Now, notice, of course, that absolute convergence is going to be a stronger condition than convergence. So absolute convergence implies that the series converges, but the other direction isn't necessarily true. Just because the series converges, it doesn't follow that it converges absolutely. In other words, the series consisting of the absolute values may not converge. And we will see examples of that, where a series converges, but it does not converge absolutely, in a little bit. So the next thing that I want to observe about actually, let's go on to talking about an example here. And in order to give you this example, we need to talk about something called alternating series. So a series is called alternating if it has the form sum from I equals 0 to infinity, or maybe 1 to infinity, or something like this, of minus 1 raised to the I times a sub I, where the a sub I are all bigger than or equal to 0. Or you could have the sum from I equals 0 to infinity of minus 1 to the I plus 1 a sub I. The point is that each term, each time we move to the next term, the sign changes. So we flip back and forth between positives and negatives as we go through this thing. Now, here's the nice thing about these alternating series. It is not true in general. So remember that the sum 0 to infinity of b sub I needs the limit as I goes to infinity of the b sub I to be equal to 0 to converge. But this is not enough. This is not a sufficient condition for convergence. For example, when we looked at the sum from I equals 1 to infinity of 1 over I, this diverges even though 1 over I goes to 0. Right, this is the harmonic series, and you saw with the integral test how this diverges. However, for alternating series, if I have the sum from I equals 0 to infinity of minus 1 to the I times a sub I, with a sub I bigger than or equal to 0, this converges if and only if the limit as I goes to infinity of the a sub i's is equal to 0. And the reason for this is not too difficult to see, but we're actually going to prove a slightly simpler but not quite as general statement. So we're going to prove the following fact. If the a sub I are decreasing, then the sum from I equals 1 to infinity, or I equals 0 to infinity minus 1 to the I, a sub I, converges if and only if the limit as I goes to infinity of these a sub I is equal to 0. Now, the proof of this fact is actually kind of intuitively, this is sort of not too difficult to understand. And the reason is, let's think about the partial sums. So we're going to list off the partial sums here for Sn. Now what's going to happen with these partial sums, if this is an alternating series that is decreasing, is this. We're going to have a situation where we start off at A0, and then we're going to subtract A1, but we're going to then add A2. And when we subtract A1, we go down, but then we come back up with A2. And the thing is, when we subtract A1, right, so this is A0 minus A1, this is going to be at A0 minus A1 plus A2. Because of the fact that this is a decreasing series, we are going to end up coming back up, but not as high as A0. And then we're going to subtract A3. But when we do that, we go down. However, we don't go down as far as A0 minus A1. We still remain above this level because of the fact that these things are decreasing. So each time we add or subtract, we change by less of a magnitude than we did last time. And therefore, the next one is going to be up here, but it's going to be below this level. And then we bounce back down, and then we bounce back up and back down. But each time we bounce less. And so what's happening is we're going to get this like maximums here and then these minimums here. And we sort of, our series is getting squeezed between these two different curves. It's getting squeezed between the lower values and the upper values. And this is really the whole proof. Like, this geometric picture is the proof. The details of it are going to be kind of, we got to write them down. There's some technical details to write down here. But really, the proof is just whatever, like, it's this picture. So the idea is, consider the partial sums Sn. And we're going to consider the S of 2n and S of 2n plus 1. So notice that 2n, this is always an even number, and 2n plus 1 is always an odd number. Now, the thing to notice is that the S of 2n's form a decreasing sequence. And the reason for that is because S of 2n plus 2 is equal to S of 2n minus a 2n plus 1 plus a 2n plus 2. And this is a negative number because of the fact that this is a decreasing sequence. Well, by the same sort of argument, we can say the S of 2n plus 1's form an increasing sequence for the same reason, because S of 2n plus 3 is equal to S of 2n plus 1 plus A sub 2n plus 2 minus A sub 2n plus 3. and this is going to be some positive number. So this is an increasing sequence and this is a decreasing sequence. But the other thing to notice is that the S of the odd partial sums bound the even partial sums from below, and the evens bound the odd from above. So the S of two n's converge as a sequence, and so do the S of two n plus 1's. Now, the problem that we still have is to show that they converge to the same thing. Well, how do we see that they converge to the same thing? Their difference is going to 0. So we know that they are both converging. We also know that the difference, S2n plus 1 minus S of 2n, is going to 0, because remember, this is actually just going to be equal to plus or minus, I forget which one, and it doesn't really matter, a sub 2n plus 1, which is converging to 0. So the difference between these two sequences is going to 0. Also, they both converge, therefore they converge to the same thing. But that means that the partial sums as a sequence in general converge, and they converge to one specific number. So this establishes our result. Now, what happens if you drop the decreasing part? Well, if you drop the decreasing part, this becomes substantially trickier, but if the limit is going to 0, then actually, I take that back. When I said earlier that the limit going to 0 is sufficient, I'm not 100% sure. Now I'm second guessing myself. Definitely, if it's a decreasing sequence and it's alternating, then if the limit of the terms goes to 0, that is sufficient. But now I want to be careful because I'm worried that maybe I could cook up some kind of weird counterexample. So let's just say that if the a sub I are not decreasing, we need to be careful. I still think in general, if the limit is 0, that we can say that this is going to be true, because the thing is, if these differences are going to 0 and they keep alternating, oh no, yeah, see, this is why you got to be really careful. Weird things can happen. Yeah, I just thought of an example where the alternating series does not converge. So the reason is because it might be an alternating series, but maybe all the negative terms become really, really small much faster than the positive terms, and then the positive terms could kind of diverge to infinity and the limit still be 0. So yeah, I take back what I said earlier. I'm very sorry about that. I got overexcited and said more than is actually true. So there are examples, and if you're really interested, I can send you more information on these examples where an alternating series has a limit of 0, but because it's not decreasing like this, it doesn't necessarily converge. But yeah, suffice it to say that in the case where the sequence of terms, the a sub i's in this alternating series, are decreasing, then we're fine. Then I know that we're fine. In fact, we just proved we're fine and this thing converges. So an example of this kind of thing is going to be the sum from I equals 1 to infinity of minus 1 to the I divided by I. Now this converges because 1 over I approaches 0 as I goes to infinity, and the 1 over I are a decreasing positive sequence. So this does in fact converge. And this is a very famous series called the alternating harmonic series. But notice it does not converge absolutely. So why does this thing not converge absolutely? Well, because if we looked at the absolute series, then this would actually just be the harmonic series, 1 over I. That does not converge by the integral test. We know it doesn't converge. And therefore, this is an example of a sequence that converges, but it does not converge absolutely. Now, here is something really weird, which we are not going to prove, but which I just want to mention to you because it's a really interesting fact. I think it's worth seeing. If you go on to take a course in analysis, analysis is the branch of mathematics that consists of things like calculus, but analysis is like sort of the technical name for all of the technical details underpinning calculus and generalizing calculus. So here is a fact. If the sum from I equals 0 to infinity of a sub I converges, but not absolutely, then we can reorder the a sub I to get any sum we want. So why is this true? Okay, I shouldn't say that we can do this in general, but actually, yeah, I think we can do this in general. But let me just say, in some cases, we can do this. And I think but I want to be careful about that, because once again, weird counterintuitive things this is counterintuitive enough. Anyway, there are cases where you can definitely reorder it like this, and I think you can do it with all of them, because here's the idea. If this converges but not absolutely, then it has to consist of some positive terms that diverge and some negative terms that diverge. But furthermore, the terms are all their magnitude has to get smaller and smaller in order for this thing to converge at all. So then what you do to get a different sum is you take a bunch of the positive terms until you get to a sufficiently large number. Like, let's say that I want my sum to come out to be bigger than some fixed number. Then I take all positive terms until I'm above that number. And then I take the first negative term, but I wait to take the first negative term until I'm sufficiently large with my partial sums that adding in the first negative term keeps me above that fixed number. And then I go back to positive terms again until adding the second negative number keeps me above that fixed number. And I keep on going like this. And by reordering the terms this way, I end up with potentially a different sum. I can make the sum as large as I want, but still converging. So it's a really weird thing that you can do this. This is very different than what we're used to with sums in arithmetic. Because in arithmetic, reordering the sums does not change the outcome. Addition is commutative and associative. So the order of operations between different additions doesn't matter. But when we start talking about infinite sums, then weird things can happen. So here is the good news from absolute convergence then. Oh, wait, hold on 1 second. Do you want to come back for this? Okay. So here's the good news from absolute convergence. If the sum from I equals 0 to infinity of the a sub i's converges absolutely, then the sum from I equals 0 to infinity of the a sub i's does not depend on the order of the a sub i's. So in other words, you can scramble the sequence and you will still always get the same sum. And that's a really nice feature. So again, we're not going to prove this. This is just a fact that I'm going to mention. But I figure, it's worth thinking about for a moment here and knowing that this is the case. Now, before we finish off here, I want to mention just a couple more examples of working with alternating series. So one more example of an alternating series. Let's suppose that we want to consider the sum, and let's do n this time. Let's say we want to do n from 1 to infinity, because of course the index that we use doesn't really matter. We can use any index that we want to. Let's suppose that we have minus 1 to the n plus 2, and then we have the square root of n divided by n plus 3. So here's what we need to do in this case. First of all, we need to observe that this is in fact going to be an alternating series. It's alternating because each time I increase n by 1, the sign flips. Now, it's not exactly what we wrote down before, but actually having minus 1 to the n plus 2, this is the same as just minus 1 to the n. Because adding the 2, well, that just multiplies by 1 and doesn't change anything. So this is, in fact, an alternating series. Also, it is easy to see that square root n divided by n plus 3 is bigger than or equal to 0, and the limit as n goes to infinity of square root n divided by n plus 3 is equal to 0. However, there is one more thing that we do need to check. We need to check that this is a decreasing series. But is it actually a decreasing series? Well, the answer is it's not obvious whether it is decreasing or not. However, it is definitely going to be decreasing eventually. And the way that we can see this is think about f of x equals square root x divided by x plus 3. Then f prime of x is going to be equal to 1/2 x to the minus 1/2 times x plus 3 minus x to the 1/2 divided by x plus 3 squared. And sorry, now I've confused myself here. Let me double check here what is going on. So this is going to be equal to 1/2 times x plus 3 minus x divided by square root x times x plus 3 squared. And this is going to be equal to, okay, I'm sorry, I'm back where I was looking. Okay, I've got it now. So this is then going to become 3 minus 1/2 x divided by square root x times x plus 3 squared. Now, this is not necessarily always negative. But for large x, this is less than 0. And therefore, this function is decreasing as long as x is large. Now, what that means about my original sequence that I'm summing is that the square root of n divided by n plus 3 is decreasing eventually. We could figure out exactly where it's decreasing by figuring out where this thing is going to be negative. In fact, this thing is going to be negative as long as x is at least 7. So this sequence is going to be decreasing for n bigger than or equal to 7. But that's enough for us to use our alternating series test, because remember, we can always throw out the first finite list of terms. I can just say, let's start at n equals 7. We'll take the first 6 terms separately, and then we'll do from 7 onwards. And that's sufficient. So because of that, we can say, yes, the original series is going to converge by the alternating series test. Because we've checked to see that this is a decreasing sequence, it does have a limit of 0, and this is an alternating series. So you'll notice that there was a little bit of work there to show that this whole thing was actually decreasing. That was kind of the trickiest part. And that is often going to be the case. And in many of those situations, you may have to throw out the first few terms to see what you actually get. One more observation. Notice that sometimes an alternating series looks weird, so to speak. So I want to give you an example here. Suppose that I have the sum from I equals 1 to, or let's do n again instead of I, from n equals 1 to infinity of the cosine of n times pi divided by n. Now, this doesn't really look like an alternating series. Where is the minus 1 to some power? Well, the fact is, notice that the cosine of pi times n is actually equal to minus 1 raised to the nth power. So therefore, this is actually the sum from n equals 1 to infinity of minus 1 raised to the n divided by n, which is the alternating harmonic series. Okay, so I want to show you this example because I want you to see that even if something doesn't immediately look like an alternating series, it could actually be an alternating series nonetheless, okay? So you want to be a little bit careful here when you're looking at something, because even if it doesn't seem like it's alternating, maybe it secretly is in some way, okay? And I'm not saying that's going to happen frequently. It's not something you can count on happening a lot, but it's something you should be aware of and that you should check for. Okay, so let's summarize the things we've done today, because we've said a few different things, and I want to make sure that you are aware of all the different things that we've said. I also want to make sure that I'm aware of all the different things I said. So we started off by talking about alternating series, absolute convergence, and then we also looked at the comparison test in the process. Now, this gives us some nice new tools for dealing with series. However, like I said, the problem with the comparison test is that it's kind of limited. Alternating series test, also very limited because it only applies to alternating series. How often are you going to deal with an alternating series necessarily? Well, depends upon what you're doing, but not necessarily all that frequently, okay? So, what we're going to want to look at is we need more tests for convergence. And most of these other tests for convergence, it turns out, are actually going to be tests for absolute convergence. The reason they're going to be tests for absolute convergence actually is more or less because in a lot of the cases, we can only apply them to positive series. But the good thing is that if something applies to a positive series, and we're dealing with a series that doesn't have all positive terms, we can still use that test to test for absolute convergence. So this is one of the reasons why people like to test for absolute convergence, because in those cases, you can always assume that your sequence that you're summing has all positive terms. And for that reason, it just simplifies things. We don't have to worry about the negatives. But anyway, so what we need more tests. Why am I saying mores? We need more tests. And that's what we're going to be looking at next time. We're going to look at more tests. So we have things where we can test for convergence for positive series, and thus can test for absolute convergence of any series. And we'll be looking at those kinds of examples because, like I said, the problem with the comparison test is that it works great when it works and it's really easy to use. However, it doesn't necessarily work all that often. The problem with the integral test is that in addition to having some minor limitations of when we can use it, it's also pretty tricky sometimes to actually calculate those integrals. And so what we really want is we want to be able to say, if I have some complicated series, is there a test where instead of trying one of these complicated tests like the integral test, can I just compare it with some other series, not with the comparison test, but compare it with some other test that is relatively simple, something where it's like a P series or a geometric series or something like that. And that's what we'll be looking at next time. But I think this has definitely gone on long enough for today, so I'm going to stop there.